2 miles beneath the Detroit River, 75 feet below the surface. The deepest underwater railroad tunnel in North America when it opened in 1910. Trains ran through it for decades. Freight cars loaded with steel and grain. Passenger cars carrying people between Detroit and Windsor. The tunnel was a marvel of engineering, a cast iron tube bored through clay and bedrock beneath an international border, moving commerce between the United States and Canada without a ferry, without a bridge, without ever touching daylight. Until July 15, 1971, when the Detroit River started coming in. Not slowly, not a manageable leak that could be patched and monitored. A catastrophic breach that flooded the tunnel in hours, filling it with millions of gallons of river water, destroying track, shorting out electrical systems, and nearly killing the maintenance crew that happened to be working inside when the wall gave way. The tunnel was supposed to be permanent. The engineers who built it in 1906 designed it to last centuries. Cast iron rings, on each one bolted to the next, creating a continuous tube that could withstand the pressure of the river above and the clay squeezing from all sides. They were right about most of it. The tunnel held for 61 years. Then geology did what geology does: shifted, settled, squeezed, and found the weak point. The story starts in 1900, when Detroit and Windsor faced a problem that ferries couldn't solve. The two cities sat across the Detroit River from each other, separated by less than a mile of water, but connected by millions of dollars in trade. Railroads on both sides carried freight that needed to cross the border. The solution was ferries, massive boats designed to carry entire railroad cars, loading them on one side, crossing the river, unloading them on the other. It was slow, expensive, weather-dependent. Ice shut down the ferries for weeks every winter. Railroad executives on both sides of the border wanted something better: a tunnel, not a new idea. The Thames Tunnel in London had been operating since 1843, the Severn Tunnel in England since 1886. Underwater railroad tunnels were proven technology, but the Detroit River presented unique challenges. The river wasn't deep, only about 50 feet at most points, but it was fast. Strong currents, heavy ship traffic, and beneath the water, the geology was complicated: clay layers, bedrock, groundwater under pressure. Any tunnel would need to go deep enough to avoid the river bottom being scoured by currents, but not so deep that construction became impossible. The Michigan Central Railroad and the Canadian Pacific Railway formed a joint venture. They hired the best tunnel engineers they could find, men who'd worked on underwater projects in England and Europe. The chief engineer, a man named W.J. Wilgus, had experience with difficult tunnels. He understood the risks. The design was straightforward: a circular tunnel, and 21 feet in diameter, lined with cast iron segments bolted together. The tunnel would run from a portal in Detroit to a portal in Windsor, descending beneath the river at a 2% grade, leveling out at 75 feet below the surface, then ascending on the Canadian side. Construction began in 1906. The method was shield tunneling, a giant circular steel shield pushed forward by hydraulic jacks, excavating clay and rock as it advanced. Workers inside the shield removed material by hand. Behind the shield, two crews installed the cast iron liner rings, bolting them together to form a watertight tube. The work was dangerous. Men worked in compressed air to keep groundwater from flooding the excavation. The pressure caused nitrogen narcosis, the bends, if decompression wasn't managed carefully. Several workers died. More were injured. The clay was unstable in places, collapsing into the excavation faster than crews could shore it up. But the tunnel advanced. slowly, a few feet per day in good conditions, less when the clay turned to muck or when they hit pockets of water under pressure. On October 16, 1910, the two tunnel shields met in the middle beneath the Detroit River. The alignment was nearly perfect, off by less than an inch. The final cast iron ring was bolted into place. The tunnel was through. Track was laid. Electrical systems installed. Ventilation fans powerful enough to clear locomotive smoke from 2 miles of enclosed space. On July 26, 1910, and the first train passed through the Detroit River Tunnel. A freight train, nothing ceremonial, just commerce moving efficiently between two countries without touching the surface. The tunnel worked exactly as designed. Trains ran continuously. Freight tonnage increased. The ferries were retired. The tunnel became essential infrastructure, invisible but critical. The kind of engineering that nobody thinks about until it fails. It didn't fail for 61 years. The problem, when it finally revealed itself, but was gradual. The clay surrounding the tunnel went static. It moved, settled, responded to changes in groundwater pressure, to the weight of the river above, to the vibration of trains passing through thousands of times per year. The cast iron liner rings were designed to handle this. The bolted joints allowed slight movement. The rings could shift a fraction of an inch without compromising the seal. It was flexible engineering, not rigid, but resilient. Except the movement didn't stop. And over decades, the clay kept settling. The riverbed above the tunnel shifted. The pressure distribution changed. And in one specific section, about 800 feet from the Detroit portal, the tunnel started to deform. Not catastrophically, not visibly, just enough that the bolted joints between cast iron rings began to separate. Fractions of an inch, not enough to leak, not yet. July 15, 1971. A routine maintenance crew was working in the tunnel, inspecting track and checking electrical systems. Standard work. They'd done it hundreds of times. At approximately 2:30 p.m., one of the crew members noticed water. Not a lot, just dampness on the tunnel wall where it should have been dry. He reported it to the supervisor. They investigated. The dampness was coming from a joint between two cast iron rings, a slow seep. Concerning, but not immediately dangerous. The supervisor made the decision to evacuate the crew and call in engineers to assess the problem. That decision saved lives. At 3:45 p.m., less than an hour after the crew evacuated, the seep became a breach. The joint failed. The pressure of the Detroit River, 75 feet of water plus the weight of the clay above, found the opening. Water came in at thousands of gallons per minute. The initial breach was maybe 6 inches wide. Within minutes, it was 2 feet. The pressure tore at the cast iron, bending the rings, opening more joints. The tunnel flooded from the breach point in both directions. Water filled the lowest sections first, and then rose toward the portals. The electrical systems shorted out. The lights went dark. The ventilation fans stopped. Railroad crews at both portals heard the alarms and shut the entrance gates, sealing the tunnel to prevent flooding into the yards. But inside the tunnel, millions of gallons of Detroit River water filled 2 miles of railroad infrastructure that had been dry for 61 years. The immediate response was containment. The tunnel was gone, flooded, unusable, possibly structurally compromised. But the portals and approaches had to be protected. Pumps were brought in to keep water from backing up into the rail yards. Engineers were called in to assess whether the tunnel could be saved or if it would have to be abandoned permanently. The assessment took weeks. Divers went into the flooded tunnel to inspect the breach and the condition of the cast iron liner. What they found was worse than expected. The initial failure had caused secondary damage. The force of the water had bent multiple liner rings. The joints that had been holding for decades were now compromised. Even if the tunnel could be pumped out and repaired, the structural integrity was questionable. The railroad faced a decision: spend millions repairing a 61-year-old tunnel that had already failed once, or build something new. They chose repair. The tunnel was too valuable to abandon. The alternative, ferries or a new tunnel, would take years and cost far more than fixing what existed. The work began in late 1971. First, the tunnel had to be pumped dry. Massive pumps ran continuously for weeks, pulling millions of gallons of river water out. Then engineers could access the damaged section. The breach was repaired by grouting, injecting concrete into the clay around the damaged liner rings to stabilize the ground and seal the opening. The bent liner rings were reinforced with steel bands. The joints were resealed. Additional monitoring equipment was installed to detect any future movement or leakage. The tunnel reopened to traffic in March 1972, 8 months after the flood. Trains ran through it again. Freight moved between Detroit and Windsor. The tunnel returned to being invisible infrastructure, but it was never quite the same. The 1971 flood revealed that the tunnel wasn't permanent. It was aging. The clay was still moving. The liner was still stressed. And while the repairs held, everyone understood that the tunnel was on borrowed time. In 1994, a new tunnel opened, the St. Clair Tunnel, a few miles north, with modern construction and better capacity. Traffic gradually shifted away from the Detroit River Tunnel. By 2000, it was used only occasionally. By 2010, it was effectively abandoned. The tunnel still exists. The portals are sealed. The cast iron liner is still down there, beneath the Detroit River, filled with groundwater now instead of trains. The 1971 breach repair is still holding, keeping the Detroit River from completely flooding the structure. But nobody runs trains through it anymore. The engineering marvel that operated for 61 years failed catastrophically. It was repaired and ran for another 22 years, finally became obsolete not because it couldn't work, but because something better replaced it. The lesson wasn't about the failure. The tunnel failed because geology is patient and infrastructure is temporary. Clay moves. Rivers press down. 75 feet of water doesn't care how well you designed the liner rings. The lesson was about resilience. The tunnel flooded. It was repaired. It ran for decades more. When it finally stopped, it wasn't because of the flood. It was because technology moved on. The Detroit River Tunnel ran underwater for 2 miles, flooded in 1971, was fixed, and kept working until it wasn't needed anymore. That's not failure. That's infrastructure doing exactly what it's supposed to do, serving until something better comes along.